Hi everybody. In this video, we're going to start learning, or you're going to start learning about the differentiation rules. So you can think of these as the shortcuts to find the derivative of a function. And we're going to start in this video with the power rule, which is one of the, I would say, most important rules, one of the rules we will use quite a bit. And I think some of you started noticing this rule when you were finding the derivative of a function as a function. Okay, so the power rule, it works like this. If f of x equals x to the n power, then f prime of x is equal to n times x to the n minus 1. Okay? This is your power rule that you want to remember. Let me give you an example. Let's say that f of x is equal to x to the 4th. So in this example, n is equal to 4. So that means f prime of x would equal 4 times x to the 4 minus 1. So then that would become 4x cubed. Okay? That's your power rule. Basically, you bring your exponent down in front and subtract 1 from your exponent. Okay, now remember that we have different notation. So this other notation, which is, this is called the derivative operator. And so basically it means that you're going to find the derivative with respect to x of x to the n power. Now the rule is still the same. Okay, that didn't change. This is just showing you this other notation. But let's look at an example. Let's say you were given the function using y instead of f of x. And so let's say it was y equals x cubed. Okay? So if we want to find the derivative, we would use our derivative operator, this d over dx. And basically, we would just put that notation in front of each side of the equation. So it's kind of like when you're solving an equation, what you do to one side, you have to do to the other. So we're going to find the derivative of both sides. Okay? So the left side, when you have your derivative operator times y, that just becomes dy over dx equals. And then you actually perform the operation on the right side. So the derivative of x cubed is going to equal 3 times x to the 3 minus 1. So in this case, your n is 3. Okay? Over here, your n was 4. All right, and then we can simplify that, and we get dy over dx equals 3x squared. Okay? So again, just, the two different notations. The power rule is the same. You move your exponent down in front and subtract 1 from your exponent. Okay, now, if you are finding the derivative of a constant, the derivative of a constant is always equal to 0. Now, there's a couple different ways you could think about it. Remember that if a function is constant, then the graph is a horizontal line, and slope of a horizontal line is 0. Or if you want to apply your power rule, you can think of this example, f of x equals 4, as 4 times x to the 0 power. So in this case, when you apply your power rule, you would end up multiplying 0 times 4, which is 0, times x, subtract 1 from your exponent, so that would be like 0 times x to the negative 1. But remember, 0 times anything is 0. So in the end, you still get f prime of x equals 0. Okay? But I just wanted to show you that, you could apply the power rule to a constant, or just remember that the derivative of a constant is always 0. Okay? All right, now we have some additional properties to help us find derivatives, and these are kind of similar to your limit laws. If you think back to your limit laws that we learned. The first one just says if you are adding or subtracting two functions, so f of x plus or minus g of x, and let's say you find the derivative of that, that's what this prime symbol means. Basically, you can split it up. You can find the derivative of f, and then add or subtract the derivative of g, okay? So if you're finding the derivative of a sum or a difference, you can find the sum or the difference of the individual derivatives, okay? And then over here, this is just showing you using the other notation. But the main takeaway is to differentiate a sum or difference, all we need to do is differentiate the individual terms and then put them back together with the appropriate signs. This is not limited to two functions, okay? All right, and then number two, this is your constant multiple rule. So if you are multiplying a constant times the function f of x, okay, and you find the derivative of it, okay, so that's the prime symbol here. If you're finding the derivative of a constant times f of x, that is equal to the constant times the derivative of f of x. So basically, you can just move the constant in front of the derivative, okay? And again, this is just showing you the other notation. But the main takeaway is we can factor a multiplicative constant out of a derivative if we need to. So if you're multiplying a constant times the function, you can just put that out in front and multiply it times your derivative. So let me show you some examples here. Okay, let's say we're given this function, f of x equals 2x cubed minus 3x squared plus 4x minus 1. Basically, to find our derivative, we're just going to differentiate the individual terms and then put them back together, okay? So f prime of x would equal, and here's how your power rule would work. You're going to take your 3, multiply it by 2. So that becomes 6x, subtract 1 from your 3. So you get 6x squared for the first term. Okay? For your second term, 2 times negative 3 is negative 6x. Subtract 1 from the 2, and that leaves you with a 1 for your exponent, which we don't typically write. And then plus, okay, right now this is a 1 for your exponent. 1 times 4 is 4. Times x to the 0 power, because 1 minus 1 is 0, and x to the 0 is equal to 1. And then the derivative of the negative 1 is 0. So we're done. That is f prime of x. Let me show you another example where we're really going to break it apart so you can kind of see how this works. Let's say we have y equals negative 5x squared plus 3x plus 2. Okay, we're going to use our derivative operator, the d over dx. Basically, we're going to find the derivative of each side. Okay? Okay, so then that means, whoops, there should be an x. Sorry. And let me erase that. There we go. Okay, so on the left side, this just becomes dy over dx, which means we're finding the derivative of y with respect to x equals. Now, we're going to differentiate each term. Okay, so initially, we're going to just kind of split this up and find the derivative of each term. Okay. And then we can apply that constant multiple rule, because here we have a constant and here we have a constant being multiplied times the functions. So we can move those out in front. So then this could become dy over dx equals -5 times the derivative of x squared plus 3 times the derivative of x plus, and I would just keep that the derivative of 2 because that's a constant, and we know that that's going to be 0. Okay, and then we're going to apply our power rule to find our derivative. So we'll end up with -5 times, apply your power rule to the x squared, and you get 2x plus 3 times the derivative of x is just 1. And then the derivative of 2, which is a constant, is 0. Okay, so then we can just multiply, and we're going to get -10x plus 3. Okay, now, the reason I'm showing you this is to really show you how these properties are applied to the derivative, kind of like we did with our limit laws, okay? But honestly, most of the time, using your power rule, you can quickly just go from here to here, okay, by just finding the derivative of each term using your power rule, okay? But I just wanted to show you one example of how these properties work. All right, now, here are a few more examples, and here what I'm showing you is that you can apply the power rule to negative exponents, to fractional exponents, and even to exponents like pi and square root of 2. So if we look at example A, to find f prime of x, again, we're just going to apply that power rule. So we're going to take the 100 and multiply it by 15. So that'll be 1500 times x, subtract 1 from your 100, so that'll be to the 99th power, minus 12 times 3 is 36, x to the 11th power, and then plus 5. All right, let's look at B. So this time we'll find g prime of t. So we'll multiply 6 times 2, which is 12, t to the 5th power. And even though we have a negative exponent, you'll still apply the power rule the same way. -6 times 7 is -42t. But when you subtract 1 from the negative exponent, you're really going to add -6 minus 1 is -7, okay? And sometimes you'll see the negative exponent left as a negative exponent, but then sometimes you'll see that simplified, meaning get rid of the negative exponent, which to change a negative exponent to a positive, you have to find the reciprocal. So this would become -42 over t to the positive 7. Okay, so you just want to be familiar with both because you'll see it both ways. All right, what I want to show you in example C is if you have a variable in the denominator, like we have this z to the 5th power, you want to use your properties of exponents and write that as a negative exponent. So before I find the derivative there, I would write y equals 8z to the 3rd power minus 1/3 z to the -5th power plus z minus 23. So all I'm doing is bringing that z to the 5th from the denominator to the numerator, and that's basically flipping it or finding the reciprocal, and it's going to change the positive exponent to a negative exponent. Okay, so then we can find our derivative and apply our power rule. So I'm going to use our derivative operator. And so we'll get dy over dx equals 3 times 8 is 24, z squared. Okay, now we're multiplying -5 times -1/3. So first of all, it's going to be positive, and then 5 times 1/3 is just 5/3. z to the negative 6, because when you subtract 1 from the negative 5, you get negative 6. Okay, and then we're going to have plus 1, which comes from the z, okay, that has a 1 in front of it. We just don't simply write it. And we're done with our derivative. Okay, for example D, what I want to show you here is if you ever have radicals, you want to convert those to fractional exponents so that we can apply the power rule, okay? So if you have the square root of x, that is equal to x to the 1/2 power. All right, then we would have plus 9 times x. I know this is hard to read, but I'm pretty sure it's a 7. So that would be to the 7/3 power. Okay, your root becomes the denominator. So that's a cubed root of x to the 7 becomes x to the 7/3. Okay, minus 2. Now, this radical is in the denominator. So we're going to convert it to a fractional exponent, which is going to be 2/5, but then we also need to bring it to the numerator. So it's going to become a negative 2/5 as the exponent. So this will be minus 2x to the negative 2/5 power. Okay, so now we can apply our power rule. So t prime of x would equal, we're going to bring the 1/2 down, so that would be 1/2 x. Okay, we're going to subtract 1, okay? But you need a common denominator, so you really subtract 2 over 2. So 1 minus 2 gives you negative 1 over 2, or you get x to the negative 1/2. All right, plus, now, 7/3 times 9. That's going to equal 21. X. Now, again, we're going to subtract 1 from our exponent, but we need a common denominator. So make that 3/3. 7 minus 3 is 4, so this becomes 4/3. All right, then we're going to multiply negative 2/5 times negative 2. So we're going to get a positive, and then 2 times 2/5 is 4/5 x. And then we're going to subtract 1 from our exponent, so that'll be 5/5. And so negative 2 minus 5 is going to be negative 7/5 as a fraction. Okay? All right, and then for example E, we have x to the power of pi minus x to the square root of 2. So sometimes, especially when we're dealing with irrational exponents, because pi and square root of 2 are both irrational numbers, we'll just apply our power rule. So we'll bring the pi down in front. So it'll be pi times x. We're going to subtract 1 from our exponent. So we'll just keep that pi minus 1, because otherwise we would have to round it, and we want to keep it exact. Okay, minus, bring the square root of 2 down in front, times x to the, when we subtract 1, we'll just keep that square root of 2 minus 1 as an exponent. I know it looks kind of weird, but it's better than, you know, having to round and make those decimals, okay? All right, so again, these examples are just showing you some different takes on the power rule and how it applies to negative exponents and fractional exponents and then even irrational exponents. Okay, now, sometimes you have to simplify the function before you can apply the power rule. So in the first example, we have 4x minus 3 squared. So here we have to FOIL first. Okay. So basically we're doing 4x minus 3 times itself. And you're probably getting a lot quicker with FOILing. So this would become 16x squared minus 24x plus 9. And then we could apply our power rule. So f prime of x would equal 2 times 16 is 32x to the first power minus 24. All right, and then for this next example, we're dividing. So we just want to divide first. Basically, you're just trying to get it to where you can use your power rule. So first of all, remember, you have to divide each term by the denominator, okay? So initially, it'll become this. But then x squared over itself is equal to 1 plus 4. Now here, we're dividing powers of the same base, so that's where you subtract your exponents. So 1/2 minus 2, we can work that off to the side. You would need a common denominator, so you could make this 4 over 2, and then 1 minus 4 is negative 3 over 2. I forgot my x. So this becomes 1 plus 4x to the negative 3/2. Okay, and that's your derivative. So that's f prime of x. No, it's not. That is f of x. We have to find our derivative still. Okay, because all we've done so far is divide by x squared. All right, so now let's apply our power rule. The derivative of 1 is 0. The derivative of 4x to the negative 3/2, we're going to multiply negative 3/2 times 4, so that'll equal negative 6x to the, we got to subtract 2 over 2 to the negative 5/2. There's our derivative. Alrighty. For the sake of time, I'm going to skip those two because they're pretty similar to the last examples. The last thing I want to show you is that sometimes you'll find your derivative and then you'll plug in a value of x. So this notation is telling you to find the derivative of x to the 4th when x equals negative 2. Okay, so the derivative of x to the 4th would equal 4x cubed. And then we're going to plug in a negative 2 for x. Negative 2 cubed is negative 8. And 4 times negative 8 is negative 32. So this would equal negative 32. And then the second example is asking you to find the derivative of x to the 2/3. And then when x equals 8. So then we'll plug in 8 for x. Okay, let's apply our power rule. So this will be 2/3 x to the, you're going to subtract 1, but you want to make it 3 over 3. And then 2 minus 3 is negative 1/3. Okay, now if we plug in an 8, this becomes 2/3 times negative 8 to the negative 1/3. Okay, now remember, to get rid of your negative exponent, you have to find the reciprocal. So this will become 2/3 times negative 1 over 8 to the 1/3 power. Or you can even think of just flipping the whole thing. If I put a 1 under that and I flip it, then that's going to become 1 over negative 8 to the 1/3 power. Okay, now remember, your fractional exponents can be converted back to roots. So this becomes 2/3 times 1 over the cubed root of negative 8. And if you're finding a cubed root, you're thinking what number times itself equals negative 8? Well, that would be negative 2. So this becomes 2/3 times 1 over negative 2. And then multiply straight across, or you can even cross reduce your 2's here. And you're going to end up with negative 1/3. And I just noticed I plugged in a -8, and that's okay. We're just going to make that a -8 in the example instead of changing all that work. All right, you guys, we're going to stop there, and we will practice this some more in class tomorrow. Have a good night.